prediction and alleviation of core gas defects using Flow 3D, a simulation software for casting industry. Note that in order for the attendees to hear this presentation effectively, the audience is muted. Again, on the right, you should see the question and answer panel of the GoToWebinar software. Please feel free to type questions through the session, and we'll address it towards the end. I'm Joel Jacob, and joining today as presenters are Cheyenne Palit and Dr. Wan Hong Yang from Caterpillar at Champaign, Illinois. We thank Dr. Yang for allocating his time to this webinar and sharing his valuable experience with the core gas model in Flow 3D. Thank you, Dr. Yang.
You're welcome. Can you hear me?
Yes, I can. Thank you. At Flow Science, Cheyenne and I have been provided with a valuable opportunity of running several simulations from prospective clients and provide technical support and training during evaluation. This has enabled a good understanding on the latest trends and the requirements of the casting industry. We would also like to thank Dr. Charles Bates of Alchemcast, a notable contributor to the model and the casting industry, for joining us during the open discussion and the question and answer session. We thank our developer, Andre Starobin. Thank you, Andre.
You're welcome.
And David Birch from Alchemcast, who has also contributed to this model.
I'm here.
Hi, David. Thank you so much for joining.
Glad to be here.
We have a good group of attendees. Thank you, everyone, for joining us today. We welcome everyone. Just to briefly describe our existence, Flow Science has been in business for 29 years. We are constantly improving and developing a versatile CFD code. We're based in Santa Fe, New Mexico, supporting client requirements in US and Canada. We also have several associates in countries like Germany, Russia, China, and a number of others. Shown here is our presentation outline. We'll start with the need for the core gas model, go over a brief example on the theory of flow science, the core gas here, simulation here, and follow with presentations by Dr. Wan Hong Yang from Caterpillar. We will also present 2 case studies from General Motors and Graham White. Finally, we will close with question and answers. Again, please type your questions in the question and answer box shown on your right. We will try to answer as many as possible during the webinar and would address it towards the end of this session. So let's take a look at why we model core gas. The primary goal here is to predict the evolution of the core gas within the core, its venting, and possibly the penetration into the casting itself, which we want to prevent. Complex castings are made by sand cores, as shown here in this example of an engine block. Resin binders are typically used to hold the sand together. When the resin decomposes, it forms gases, and these gases have a potential of penetrating the metal. The core gas model simulates the behavior of these gases that appear in sand forms from organic binders when the sand is heated by the metal. These gases can build up enough pressure to blow gas into the liquid metal, thereby causing porosity defects. The model describes the formation and flow of these gases into the porous cores and mold, the pressure distribution inside the sand, and the amount of gas, if any, that escapes into the metal. Let's take a look at a simple example to understand the core gas model. Shown here is a spherical core that is positioned in an initially empty cavity and then filled with liquid metal. On the right, you can see pressure contours that show the distribution of the pressure within the core and the metal during the filling process. What we are seeing is a snapshot of pressure distribution during the filling. The vectors here show the metal and gas velocities. As the core is heated, the gas pressure inside builds up. At the same time, the metal hydrostatic pressure outside the core increases as the cavity fills, which you can notice here. Typically, it is a race between the 2 processes. If the metal pressure builds up faster, there will be no gas blow into the metal, which is what we want. We'll take a quick look at the implementation of the core gas model in Flow 3D. Shown here is the Flow 3D interface. Let me briefly go over it. We have some main tabs on the top for the model setup or the pre-processing, the solver, and as well as post-processing. In addition to the typical casting setup, the core gas model is activated under the Physics tab. So under Physics, we have a lot of physical models that could be enabled. Core gas model is one of the options. Shown here is the option that shows up when you enable the core gas model. So you can activate the model and the print venting. We have some numerical options available. Then you move on to the meshing and geometry panel, which is what you see here. Shown here is the components of a casting process where we are studying core gas. The core gas properties are entered over on the left tree structure here. So the properties such as the core gas porosity, the core gas density, binder weight, and the composition, the gas properties, etc. can be set. Another great feature is to have selected output data. So we could go to the output tab and select some data that you would want to observe in transient analysis at a certain time interval. So you could look at selective data like the core gas surface flux or velocity or the binder weight fraction distributions. Then we have several results for core gas, such as the core gas flux, the binder weight fraction, or the outgassing rates that could be analyzed as well. You could make 3D animations or snapshots of it, or even look at it at 2D sections or take data out. At this point, I'll pass the presentation to Dr. Yang so he could go over his experience at Caterpillar with the core gas model, and then we will follow up with 2 more case studies from General Motors and Graham White. Thank you, Dr. Yang, and I'll just pass the presentation over to you right now.
I want to thank you guys, give us the opportunity to show this. Me and Rick have been working on this only for a very short time. If you look at what I put here, said that we have limited experience on this. Really what I mean is really before I use this for the core gas simulation, I do have unlimited experience with Flow 3D itself, even though I've been using it for quite a few years, but each year I probably spend a few hours on it. And with this core gas, we only started in, I think it's middle of July after you guys finished this MacWasp meeting. So we actually run it, use Windows machine, and use the beta version Flow 3D provided to us. Really, each run usually takes about half a day to maybe 2 days time frame, depending on the complexity of your model. The test case we did is engine head with the cores inside. Also, sometimes we include the mode, sometimes we don't. So it depends on the situation. And if we don't include the mode, we just have the cores itself and with some artificial feeding conditions. I think it looks like this is a pretty good way to study individual cores, see what's their behavior during feeding and gassing. We basically used, in this presentation, most data actually was produced with the default Flow 3D information, like the binder content, the core porosity, and the density. The mesh size generally looks like it really needs to be very fine. The reason is because core gas depends on the heat penetration inside the sand, and inside the sand you usually have very steep thermal gradient. You have to use a finer mesh to resolve that temperature field. So that's, I think, it's a limitation so far in the software. So that's why the runs usually takes much longer. Here I show a movie of the feeding. On the left, the metal rises in the mold cavity, and on the right, you can see the core assembly where it starts degassing and the gas comes out from the surface of the cores at each different stage. And when the metal feels higher, you build more hydrostatic head, which suppresses the core gas. That's why initially the cores at lower position gas, and at a certain point, when the metal head is high enough, then it suppresses the flow outgassing into the metal. So that's what you see here. I will let it run another time, and then I can move on to the next page. I think these two movies are synchronized. Left-hand side is the metal hide, and the right-hand side is the gas in the core. Yeah, you can see certain spots inside the core, they really have a lot more gas than other spots. Generally, usually the gassing spot is relatively thinner sections inside the core. Okay, I'll move on to the next page. This one is an abstract view of what's happening to the core. Overall, how much gas was generated, and then how much gas is flowing into the mold cavity, and how much actually gas emitted into the liquid metal, and at which stage during the finning most gas is generated. And at the end of finning, is there any more gas still emitting from the cores? This page shows the gas pressure inside the core after the mold is filled. I think a good way to look at it is really you look at the core gas pressure and at the same time see how much metal head in your mold. You can do the conversion, use this simple equation and try to do a conversion like liquid metal, 1-inch liquid iron here probably equals about 1600 megapascal. That means with these numbers you need about 8 to 9 inch of liquid head to suppress all the core gas. And this for the default data I've used about 1% of binder content in there. In real life situation, maybe we have the core resin percentage is slightly differently. You can see the core gas pressure inside the core is like this. When the mold is full, you really you need about maybe around 20-inch metal head to really suppress any core gas. That means most likely during the finning you have a lot of bubbling, and even after end of finning you still have bubbling. If generally I think during finning you have a gas bubble, is probably slightly less concerned. Especially when the mold is full, you may form some kind of skin on the top, and then you have gas bubble form underneath. That will be a problem. If you do something like put a very simple vents in here, very small diameter holes in here, you can really relieve the pressure a lot. This one probably only needs about a couple of inch head to suppress all the core gas, and this one needs about 20-inch head. So that you can see the magic tool help you understand what's the most effective vents. I think we have tried this simplistic case, put a hole in here, drill through this core prints. But I think we actually see in reality you can do a lot more things than this and understand how to route your gas out from the core much better. This page shows the heat thermal penetration of the inside into the center core. What I want to really show here is if you look at really this software can also help you to understand about physics, what's the most important factor to consider when you look into your core package. Look at this really the heat is driving all the decomposition and the gas pressure, and the gas pressure is driving force for the core gas flow. And if you do have, let's say on the outside of the mold, you have a lot of volume, even you create the pressure, the gas, but because the gas is compressible, if you have a lot of volume to contain them, you may not really have problems. Really what's causing problem is some of the cores which is thinner and intermediate size, which can be heated through quickly and create a lot of gas pressure, and it doesn't have a lot of volume to contain them. So that's where you will likely have problems. It also shows the thermal penetration during finning is really very thin cross in there, and maybe with that we can also develop some kind of simpler model for just a quick early look of the cores. So with that, I think I'm coming to the final page of my presentation. I think generally we have very limited experience, but so far we have seen this is a great tool we can use to solve foundry problems. And we still have a lot of learning to do, how to set the cores and how to select the property. When you build the geometry, questions concerning to the venting, especially the parting lines, and a lot of conditions cannot be really very well represented in the geometry model. I think that's something we need to look into to get a better understanding, because a lot of times you receive the model and really you don't get the full picture of what's happening in the shop. For the development side, I do have several recommendations to Andre. Maybe you can look further and help to define it even better, like solve the fine mesh constraints. Right now, you have to use a finer mesh to do the core gas, and not for the thinning, but for the core gas. And when you do the core gas coupled with thinning, you do need to solve a huge amount of computational load. So that's something you need to look into for the future. And also, is it possible to develop some kind of a very quick, dirty model, just like I said, since heating is just a skin effect, maybe you can do something like a modulus type of approach, like cast metals, and really without doing this extensive simulation, you can really look at the core gas behavior of the cores. Also the bubbling behavior and the quality, because being asked, say you say you are core gassing, but where does those bubbles go, and how do I know this bubble is actually from this core? Of course, there are some suggestions from Andre, say what's the way you can do experimental to verify that. I think if we have some numerical tool to help understand that, I think Flow 3D probably has a very good possibility can do that. Put some bubbles in there and see how it goes, where the flow up to and where it freeze off and stay in there. I think the model, to me so far, is a very good model. If we can also consider some like the coating effects, capillary force forming, I think usually the model right now so far assumes if the gas pressure is higher than liquid pressure, then you form the bubble. We know when the bubble forms also you need to overcome a lot of these surface tension factors and other factors. I think if we can consider that, probably more realistic. So far, this model solution, I think, is always conservative. So it's a good thing, at least we have this tool. At last, I want to acknowledge, thank Andre and Melissa for the support, and also Flow Science to make this beta version available to us for the trial. And thank you all.
Thank you, Dr. Yang. Thank you again, Dr. Yang. That was a wonderful presentation. Good morning, everyone. My name is Shayan Palit, and I'm an engineer here at Flow Science. I'll talk about simulations done for an engine block water jacket core at General Motors. I'll go over these images in the clockwise direction. The first image here on your upper left-hand side shows the jacket and slab assembly. The figure on your right-hand side here shows the jacket core with the vents. You can see the vents, they are holes drilled into the core. The jacket core leg below is a zoomed-in view. And the figure on the bottom left here is a zoomed-in view of the core print in the slab. PUCB, 1.3% PUCB, which stands for phenolic urethane gold box, was used as the binder for these simulations. And the silica sand used in the core had a grain fineness number of 63. A submersion test was conducted at GM on parts of a V8 A319 engine block. Both vented and unvented jacket cores were placed in the open flask mold, which you can see in the video, and bottom filling was done in about 20 seconds. In venting cores, the venting was provided with holes drilled from the prints. These holes were 3 millimeters in diameters and up to and about 90 millimeters in length. The video that you just saw shows the top view of the fill for the unvented core. I'll play it again. You will note that a row of bubbles was produced after the bottom of the jacket core submerged. This happens at about 8 seconds into the simulation or into the video, and another row of bubbles are formed approximately 15 seconds from the beginning. All these bubbles are suppressed at a metal depth of 7.5 centimeters above the core peak. This image on the right-hand side points out the location for the second set of bubbles. This video here shows the top view of the fill for an unvented core. No gas bubbles were observed above the core during this fill. Also, please note, like Joel mentioned before, I would like to remind all of you that you can type in your questions in the Q&A box on the right-hand side, and we'll get to these questions at the end of the presentation. The slide here shows the simulation setup. This view shows the core contained in the mold flask. This is the setup with the mesh block, which allows us to isolate a region of the core in the mold. And on your right-hand side, we have the meshed region, which is our domain of interest. This slide shows simulation results for the unvented core. The animations show sectional views of the geometry for this unvented core. On your left-hand side, we have the animation for the core gas surface flux. I'll play this animation now. Dark blue indicates the zero core gas flux, and red indicates the maximum core gas flux on the surface of the core. The vectors are used to indicate the core gas moving within the core. And loss of gas into the metal is visible at the top and bottom portions of the top half of the jacket core. And the gas flow occurs at sites which have the lowest metal static head. Additionally, you can see desirable gas venting occurring at the prints into the mold flask. Let me show you these regions in detail now. You can see these lighter regions, which indicate regions where gas is blowing into the metal. And here we have venting occurring into the mold from the core. The animation on the right shows the binder weight fraction at a cross section as a function of time. The core initially has a binder weight fraction of 1% uniformly everywhere. As the metal fills in the cavity, we can see that the binder weight fraction decreases closer to the outer surface of the core as the binder vaporizes into gas. You can see that the weight fraction has reduced all around the edge of the core here. This slide here shows the results for the vented core this time. I'll wait until the audience can see the screen as well. Okay, so the slide here again shows the results for the vented core. The animation on the left-hand side shows the core gas flux at the surface of the vented core. This sectional view shows one of 3 vents which are present in our domain. Like we saw in the previous slide, colors different from deep blue indicate non-zero values for the core gas flux. The animation on the right shows the core gas blowing into the metal as a function of time. The figure here shows the core gas mass flow rate and the gas flow rates for the two designs. The cumulative flows can be computed from a plot like this. As you can see, the vented core shows significantly lower gas flow rates during the submersion of the bottom portion of the core and a complete suppression of the gas flow after 15 seconds. You can see this is the gas flux to the metal for the vented case. There's almost a complete suppression of the gas flow into the metal after 15 seconds. The computed result is in good agreement with the experimental observations, especially later in the fill when the gas flow is almost completely suppressed. The gradual increase of the gas flow from the unvented core is also in agreement with the foundry observations, and this is the curve for the unvented core. The two peaks that you see here, peak 1 here and peak 2 here, roughly correspond to the two sets of bubbles seen in the experiments. I'll now pass the presentation back to Joel, who will go over the Graham-White iron valve simulation. Joel?
Thank you, Shane. That was a good presentation. Very nice set of animations there as well. So shown here is an iron valve casting setup. We'll now compare two cores and see how Flow3D can be used to show which core is better. Two shell sand cores were compared using Flow3D here by Graham-White Manufacturing. We have Elizabeth Ryder from Graham-White joining us. Thank you, Elizabeth. The illustration on the right shows the simulation setup with the sprue, the porous filter, and the cast cavity containing the T and saddle core shells. Again, we are using two cores here, a T core shown at the bottom of the screen and a saddle core. Note that the simulation was done using the geometry from the cavity containing the saddle core and the T core without requiring separate geometries for the core. To actually understand this better, I have two snapshots here. So shown on the top left here is the actual cavity that's cast. On its right, you can see a cutting plane in Flow3 that shows the hollow sections of the T and saddle cores. Notice the walls around here of the saddle core. And the image at the bottom is the actual cores shown against the scale. Note that the saddle core has no drilled holes to relieve the core gas pressure and vents through each of its prints. However, the T core has a hole drilled through its center. It's visible on the screen here. I'll probably use a highlighter in this case. This design allows the T core to vent through the central hole into one end of the cross-sectional piece. There's a slight lag in relay here, so I'll wait a second here. Shown on the screen is the actual T and saddle cores used in the foundry. On your right, you can see the pressure contours of the metal filling process through the sprue, passing the filter, and then filling both the cores and the cavity. I'll play this animation again. What we're seeing here is the pressure contours, higher pressure being in the sprue head here, where the cavity is being filled along with the cores. Again, as a reminder, if you have any questions, please feel free to type it in the question and answer box so we can address them towards the end of this presentation. Shown here are the results with the binder weight fraction on the cores and the core gas flux. I'll play these animations shortly here. Notice on your left is an animation, and the results shown on the screen is a final snapshot of the binder weight fraction. As the binders decompose into gases and escape, the binder weight fraction reduces. Let's take a look at the animation. We're marching through time here, shown by the time frame. And you'll notice how the binders decompose into gases and escape. Let's now take a look at the result on the right here, which is the core gas surface flux. Now, ideally, the core gas surface flux should show venting through the prints into the atmosphere. As you can see here, shown by the yellow regions of the T-core, which goes into the prints and out into the atmosphere. However, in this particular case, it is clear that the higher concentration of the gas flux is at the saddle core surface that presents the risk of gas blowing into the metal, thereby causing porosity defects, which is undesirable. So let's take a look at this animation as well. I'll play it. Now let's take a look at the pressure contours. Shown here is animation. You can notice the higher pressure buildup on the saddle core. It is clear that the T-core builds up pressure closer to the prints, so it can be vented through the prints. However, the saddle core has higher pressure showing on its upper surface that could present the risk of blowing into the metal. Let's play this animation. It is quite clear now that the saddle core presents higher risk of the gas blowing into the metal as opposed to the T-core, which generates the pressure closer to the prints and is a better design. Having seen the core gas modeling in Flow 3D, let's take a look at what other aspects of Foundry could be modeled using Flow 3D. So we could model filling aspects, such as the maximum gate speeds that are important for the light loss, so they do not exceed the recommended values. We can find the amount of entrained air quantitatively, as well as predict the surface oxides and defects. In addition, you can obtain the solidification time, analyze closely the directional solidification, choose the superheat temperature for a given casting to avoid the freezing of metal during the fill. We can also detect the hot spots, predict macroscopic shrinkage, porosity, and also microporosity due to the entrapped gas or air. To summarize this presentation, a new core gas model in Flow 3D computes the generation, transport, and the venting of binder gases. Dr. Yang of Caterpillar shared his results of core gas flow in ion engine head cores. Simulations of the vented and unvented water jacket cores show good agreement with the GM Foundry results. In multi-core molding assemblies, as seen in the gram-wide casting, problem cores can be identified. This brings us to the end of this presentation. Shown on the screen are contact information to Cheyenne and myself. Please feel free to contact us to schedule a demo specific to your application. Again, thank you all for attending this presentation. Have a nice day.